One of the areas that scientific notation is really useful in is in biology, whenever you're trying to describe something that is very, very small. Scientific notation can be used to take a very, very tiny number and write it more concisely, mostly so that it's easier to read. If you look at our first example, the average size of an atom is about, and then it has a decimal point and a bunch of zeros, and it can be really hard to even tell how many zeros there are. If you start to count, sometimes they sort of blur together because there's so many zeros. Scientific notation can help us identify exactly how many zeros there are to know exactly what number we're dealing with. So the average size of an atom is about 0 point, and it looks like a handful of decimals, 3 centimeters across. Write the average size of an atom in scientific notation. So just like whenever we were taking a very large number and writing it in scientific notation, when you take a very small number, the beginning process is the same. We start with the number that is at the end of all the zeros, which in this case is the number 3. So let's start with a 3, and just like before, we're going to multiply it by some power of 10. So times 10 raised to some power. Now the power is how many times would we have to move the decimal to get from where it is after the 3, where we put it at the end of the 3 so that we had the whole number 3, to where it was originally in the number right there after the first 0. How many times do we have to move the decimal? So let's count. We'd have to move it 1, 2, 3, 4, 5, 6, 7, 8. We'd have to move the decimal 8 times. So we are not going to put an exponent of 8 up here. And the reason we're not going to put an exponent of 8 up here is because 3 times 10 to the 8th means write a 3 with 8 zeros after it, which is a very, very large number. We want to write a very, very small number. We want to write a decimal 7 zeros and then the number 3. So how do we indicate that instead of a very, very large number, a 3 with 8 zeros, we mean a very, very small number, a decimal, 7 zeros, and a 3? And the answer is we make the exponent negative. 3 times 10 to the negative 8 power. The negative number indicates that our value is very, very small. You can think of it like a negative exponent means that we are moving the decimal to the left to make the number smaller, and a positive exponent means that we are moving the decimal right to make the number bigger. So, positive exponent means a large number, negative exponent means a small number, right? I want you to also notice, let's go back real quick to this problem, that 3 times 10 to the positive 8 power would be a 3 with 8 zeros. 3 times 10 to the negative 8 power means a decimal point and then only 7 zeros and then the 3. And the reason it's only 7 zeros instead of 8 is because the first time we move the decimal, it's to get on the other side of the 3, right? The decimal was on the right side of the 3, and we move it once to the left side of the 3 and then start adding zeros. So the number of zeros in front of our digit is always going to be off by 1 from the exponent. So keep that in mind as you're working these. Okay, so 0.0000829. So 4 zeros and then 829 after the decimal. So let's take a look at our numbers that are after all the zeros, and those numbers are 829. And just like any other kind of scientific notation, we put the decimal in such a place where our number is between 1 and 10. That means our decimal goes after the 8. Now we ask ourselves, how many times would we have to move the decimal point to get from where it is after the 8, where we put it, back to where it is in the original number? And that's what our power of 10 is going to be. So let's count. To move it from after the 8 to the original spot, we move it 1, 2, 3, 4, 5 times. So 5 times we had to move that decimal. So it's going to be 10 to the negative 5th power because we moved the decimal point to the left to make a very small number, 0.0000829, very small number. That's why it's to the negative power. Okay, so there it is in scientific notation. Okay, let's do another example. This one is 0.0000000302. So we've got 6 zeros, 302. So let's look at our numbers that are after all of the zeros. That would be the 302. So we do 302. And then we're going to put our decimal in a spot that makes this number 302 in between 1 and 10. So let's go ahead and put it right here, 3.02. And what power of 10 are we going to multiply it by? So we put our decimal here after the 3. How many times do we have to move it to get it back to the original spot? Let's count. 1, 2, 3, 4, 5, 6, 7. 7 times we had to move the decimal. Again, there are 6 zeros, and we had to move the decimal 7 times. So our power is going to be to the -7th, because that's how many times we move the decimal point. So -7 means decimal point, 6 zeros, and then our number. Okay, last one. A typical red blood cell in human blood has a diameter of approximately 0.000007 meters. Write this diameter in scientific notation. So we have a decimal point, 5 zeros, and then a 7. So we're going to start with our 7, and we're going to multiply by 10. There's a decimal point and 5 zeros. So the power that we're going to raise it to is going to be what? The decimal was here. We go 1, 2, 3, 4, 5, 6 times we move that decimal. And because we're moving it to the left to make a small number, our exponent is negative. So 7 times 10 to the -6th power. And that is going to be our 0.000007 meters in scientific notation.